Problem 611 asks to calculate the diffusion coefficient at one temperature when given that diffusion coefficient at another temperature, and also given the activation energy for the fusion of copper in silver. So we're going to use the diffusion coefficient equation, which is D equals the pre-exponential D naught times E to the negative QD over the gas constant R times the temperature T. Now, again, this is the diffusion coefficient. D naught is pre-exponential. E is E, and QD is the activation energy. R is the gas constant, and T is the temperature, but this must be the absolute temperature. We're also going to use the inverse of this. So if I divide both sides by this term, we can write D naught, the pre-exponential, is equal to D times E to the QD over RT. The minus sign up above simply means that this term, E to the QD over RT, is actually the inverse, so it's on the bottom. So if I divide it by itself, then it comes back on top on the other side. Okay. Now we're given 2 points. One is the diffusion coefficient, or one is at a temperature of 1000 K, and the other one is at 1200. Now we don't know the diffusion coefficient at 1200, but we're given it at 1000. So at 1000 it's 1 times 10 to the negative 14th. 1 times 10 to the negative 14th, and that is in meters squared per second. And the pre-exponential is also, the pre-exponential is not given, but the activation energy, QD, is given, and it's 193 kilojoules per mole. So this is all the information that's given, and ultimately the question is, what is this diffusion coefficient here? What we need to do is use our equation to find the pre-exponential. Once we find the pre-exponential, we can put that value into the same equation at 1200 degrees. Now, the activation energy is the same for both. So this should be 193. So once we find, once we use the equation, find the pre-exponential. The pre-exponential should be the same thing for both, with the pre-exponential in here, and then we can find the diffusion coefficient at 1200 degrees. And this is again all for copper going into silver. Okay. Let's start off with, again, we don't know dO, pre-exponential, so I'll use that equation first. Pre-exponential equals the diffusion coefficient times e to the negative qd over RT. And with what's given, we have 1 times 10 to the negative 14th times e to the negative qd. Q is 193 kilojoules per mole, all over R, gas constant, is 8.314 joules per mole degree Kelvin. And then also on the bottom is the temperature, and that is 1000 degrees Kelvin. Alright, let's cancel our units out, making sure we've got everything. Okay. Degrees Kelvin, moles, joules, make sure you take this K and multiply by 1000. So it's going to be 193,000 up on top. So all these units up here canceled, and what we're left with is that of the pre-exponential, which is meters squared per second. So the pre-exponential is 1.22 times 10 to the negative 4th meters squared per second. So got that there. Okay, now we can use it for this equation. So for 1200 degrees Kelvin, the diffusion coefficient at 1200 is equal to the pre-exponential times e to the negative qd over RT, and the qd is going to be the same, 193 kilojoules per mole. R is going to be the same, 8.314 joules per mole degree Kelvin, and the temperature is going to, this time, going to be 1200 degrees Kelvin. So we use the pre-exponential that we just calculated, 1.22 times 10 to the negative 4th meters squared per second times e to the negative 193,000 joules all over 8.314 joules per mole degree Kelvin times 1200 degrees Kelvin. Put that all in parentheses. So that ends up calculating out to 4.80 times 10 to the negative 13th meters squared per second. And that is our final answer. One note. So this problem successfully shows that you can take one point of knowledge, calculate a common constant for another point, then apply it, and then find its diffusion coefficient.